The image arrived at 0300 UTC on November 2nd, 2025, and within minutes, the night shift astronomers at the European Southern Observatory knew they were looking at something that shouldn't exist. The Very Large Telescope's adaptive optics system had captured 3I Atlas during what should have been a routine monitoring pass. But the processed data showed something that made 3 separate analysts check their calibration settings before alerting their supervisor. The nucleus wasn't irregular. It wasn't the lumpy potato-shaped mass that every comet, asteroid, and interstellar visitor in history had shown us. Instead, the enhanced resolution revealed edges, straight edges, meeting at precise angles that formed what appeared to be a near-perfect hexagonal structure embedded in the comet's heart. The measurements came back immediately. 6 sides, each spanning approximately 4.2 kilometers in length. The angles between edges measured within 0.3 degrees of the theoretical 120 degrees required for geometric perfection. At the scale of a mountain across the hostile environment of interstellar space, something had maintained geometric precision that would challenge human engineering on Earth. Protocol demanded skepticism first. The team spent 2 hours methodically eliminating every possible source of error. Instrumental artifacts from the adaptive optics system were ruled out by examining calibration stars that showed normal, irregular brightness distributions. Atmospheric distortion couldn't explain it because 3 independent processing algorithms revealed the same hexagonal structure. Data corruption seemed impossible when the raw photon counts clearly delineated the edges in unprocessed form. By 0600, the Gemini North Observatory in Hawaii had repositioned to capture its own images. Different hemisphere, different telescope, different atmospheric conditions, yet the geometry remained. The hexagon persisted with the same dimensions, the same angles, the same impossible regularity. Word spread through the astronomical community with unprecedented speed. Slack channels exploded with activity. Email servers strained under the weight of attached image files being shared between observatories. By midday, 14 separate facilities had confirmed the geometric structure, using everything from ground-based telescopes to archived Hubble data that, when reprocessed with the new understanding, showed hints of the hexagon that previous analysis had dismissed as noise. The statistical analysis landed like a hammer. Natural geological processes could create straight lines through fracturing and crystal growth. Magnetic fields could organize particles into regular patterns. But the probability of random natural forces producing 6 equal-length edges meeting at precise angles, maintaining that structure across months of observation, while the object tumbled through space and sublimated thousands of tons of material, came out to approximately 1 in 10 billion. 3I Atlas had just transformed from an anomalously massive interstellar comet into something that defied every natural formation model in planetary science. The geometry was real, it was stable, and nobody could explain it. The image arrived at 0300 UTC on November 2nd, 2025, and within minutes, the night shift astronomers at the European Southern Observatory knew they were looking at something that shouldn't exist. The Very Large Telescope's adaptive optics system had captured 3I Atlas during what should have been a routine monitoring pass. But the processed data showed something that made 3 separate analysts check their calibration settings before alerting their supervisor. The nucleus wasn't irregular. It wasn't the lumpy, potato-shaped mass that every comet, asteroid, and interstellar visitor in history had shown us. Instead, the enhanced resolution revealed edges, straight edges, meeting at precise angles, that formed what appeared to be a near-perfect hexagonal structure embedded in the comet's heart. The measurements came back immediately. 6 sides, each spanning approximately 4.2 kilometers in length. The angles between edges measured within 0.3 degrees of the theoretical 120 degrees required for geometric perfection. At the scale of a mountain, across the hostile environment of interstellar space, something had maintained geometric precision that would challenge human engineering on Earth. Protocol demanded skepticism first. The team spent 2 hours methodically eliminating every possible source of error. Instrumental artifacts from the adaptive optic system were ruled out by examining calibration stars that showed normal, irregular brightness distributions. Atmospheric distortion couldn't explain it because 3 independent processing algorithms revealed the same hexagonal structure. Data corruption seemed impossible when the raw photon counts clearly delineated the edges in unprocessed form. By 0600, the Gemini North Observatory in Hawaii had repositioned to capture its own images. Different hemisphere, different telescope, different atmospheric conditions, yet the geometry remained. The hexagon persisted with the same dimensions, the same angles, the same impossible regularity. Word spread through the astronomical community with unprecedented speed. Slack channels exploded with activity. Email servers strained under the weight of attached image files being shared between observatories. By midday, 14 separate facilities had confirmed the geometric structure, using everything from ground-based telescopes to archived Hubble data that, when reprocessed with the new understanding, showed hints of the hexagon that previous analysis had dismissed as noise. The statistical analysis landed like a hammer. Natural geological processes could create straight lines through fracturing and crystal growth. Magnetic fields could organize particles into regular patterns. But the probability of random natural forces producing 6 equal-length edges meeting at precise angles, maintaining that structure across months of observation, while the object tumbled through space and sublimated thousands of tons of material, came out to approximately 1 in 10 billion. 3I Atlas had just transformed from an anomalously massive interstellar comet into something that defied every natural formation model in planetary science. The geometry was real, it was stable, and nobody could explain it. The geometry demanded precision measurement, and within hours of confirmation, research teams across 3 continents began the painstaking work of quantifying exactly how perfect this hexagon actually was. The results would either reveal subtle irregularities that pointed toward natural explanations, or they would deepen the mystery into territory that made even veteran astronomers uncomfortable. Edge length measurements came first. Using multiple observation epochs spanning October 15th through November 2nd, 2025, analysts tracked the hexagon's dimensions with sub-pixel accuracy. The 6 edges measured 4.18, 4.21, 4.23, 4.19, 4.20, and 4.22 kilometers respectively. The variation between shortest and longest edge was just 50 meters across structures spanning more than 4 kilometers, a deviation of only 1.2%. To understand how remarkable this uniformity is, imagine trying to build a hexagonal structure the size of a small city where each wall deviates by less than the length of an Olympic swimming pool. In human construction, that would require laser-guided precision and constant maintenance. 3I Atlas had maintained this precision while traveling through interstellar space for potentially millions of years. The angular measurements proved even more startling. Using high-resolution astrometry to map vertex positions, researchers calculated the internal angles where edges met. Theoretical perfection required exactly 120 degrees at each corner. The measured angles came in at 119.7, 120.2, 119.9, 120.1, 120.0, and 119.8 degrees. Maximum deviation from perfect geometry was 0.3 degrees. That's roughly the width of a pencil held at arm's length, across a structure kilometers wide, tumbling through space at 20 kilometers per second, subjected to thermal stresses from solar heating and outgassing forces strong enough to create visible jets. The geometry held. Surface texture analysis revealed another puzzle. The edges appeared smooth at the resolution limit of current telescopes, showing no signs of the fractal roughness that characterizes natural geological features. Every cliff face, every crater rim, every natural edge in the solar system shows irregularity when examined closely enough. Coastlines become more complex the closer you zoom. Mountains reveal texture at every scale. But 3I Atlas's edges remained geometrically pure, down to the 10-meter resolution threshold. The symmetry extended beyond simple edge lengths. The hexagon's center of geometric symmetry aligned within 200 meters of the photometric center, the brightness-weighted average position of the entire coma. Either random natural processes had created perfect geometric and optical alignment by cosmic coincidence, or something else was organizing matter around a deliberate structural framework. The probability calculations kept getting worse. Natural geometry was officially in crisis. Scientific discovery demands skepticism, especially when observations challenge fundamental understanding. The hexagonal structure in 3I Atlas violated so many expectations that verification became the astronomical community's immediate priority. If this geometry proved real, it would rewrite textbooks. If it proved false, it would become a cautionary tale about premature conclusions. The next 72 hours would determine which path history would follow. Independent verification began with raw data sharing. The European Southern Observatory released unprocessed photon counts to 23 research institutions on November 3, 2025, including facilities that had no prior involvement with 3I Atlas observations. These teams applied their own reduction pipelines, calibration methods, and analysis software. If the hexagon emerged only from specific processing choices, these independent approaches would reveal different structures or none at all. Every team saw the hexagon. Princeton's analysis, using conservative smoothing algorithms, showed the same 6 edges. Caltech's aggressive noise reduction protocols revealed identical angular measurements. The Tokyo Observatory's completely independent software suite, built on different mathematical foundations, reconstructed the geometry with variations under 0.5% from the original measurements. The instrumental artifact hunt intensified. Could the telescope's hexagonal secondary mirror support structure create phantom geometry through diffraction? Tests on calibration stars with known irregular shapes showed no hexagonal artifacts. The support struts would create 6-fold symmetry in point sources. But 3I Atlas was an extended object spanning dozens of pixels. The geometry appeared in the object itself, not in the telescope's optical signature. Atmospheric distortion received similar scrutiny. Earth's turbulent atmosphere can create spurious structures through random phase variations in incoming light. But adaptive optics systems correct for these distortions in real time, and the hexagon appeared identically in both corrected and uncorrected images when processed appropriately. Multiple observatories at different latitudes, looking through completely different atmospheric columns, all confirmed the same structure. The wavelength independence test provided crucial validation. If the hexagon resulted from some peculiar interaction between dust grain sizes and optical light scattering, it should disappear or change dramatically at other wavelengths. Infrared observations from the James Webb Space Telescope showed the hexagonal structure clearly. Ultraviolet data from archived Hubble observations, when reprocessed with enhanced techniques, revealed the same edges. Radio observations detecting molecular emissions showed geometric organization matching the optical hexagon's orientation. Temporal stability sealed the verification. 3I Atlas rotates with a period of approximately 18 hours. As the object tumbled, presenting different faces to Earth-based observers, the hexagon remained visible and geometrically consistent. This ruled out perspective illusions that might create apparent geometry from irregular structures viewed at specific angles. By November 5th, the consensus was unavoidable. The hexagon was real, it was physical, and it demanded explanation. The verification protocol had failed to find any conventional reason to dismiss what telescopes clearly showed. The impossible had become merely improbable, and science needed answers. Understanding what the hexagon actually represents requires separating the physical nucleus from the surrounding coma, the vast cloud of gas and dust that makes comets visible. The geometry could exist at multiple scales and in multiple forms, each possibility carrying radically different implications for 3I Atlas's nature and origin. The most conservative interpretation places the hexagon as a surface feature on the solid nucleus itself. High-resolution imaging suggests the edges correspond to physical boundaries in the reflective material, possibly ridges or escarpments rising above surrounding terrain. If true, this means solid rock or ice has been carved or formed into geometric perfection, spanning more than 20 square kilometers of surface area. Scale becomes crucial here. The nucleus measures at least 5 kilometers in diameter, based on mass estimates, making the hexagon large enough to cover nearly the entire visible hemisphere. It's not a small feature or local anomaly. It dominates the object's structure at the largest observable scales. Orientation analysis reveals another puzzle. The hexagon's plane sits tilted approximately 37 degrees relative to 3I Atlas's orbital plane. This orientation remains stable despite the object's 18-hour rotation period, suggesting the geometry is fixed to the body rather than some transient phenomenon in the surrounding gas. As the nucleus tumbles, the hexagon tumbles with it, maintaining its precise angles and edge lengths. The coma organization provides an alternative interpretation. Perhaps the hexagon represents structured dust and gas rather than solid surface features. The outgassing jets detected earlier could be organized along the geometric edges, creating apparent structure in the surrounding material, while the nucleus itself remains irregular. This would explain how the geometry persists despite continuous sublimation, removing thousands of tons of material daily. But spectroscopic analysis complicates this comfortable explanation. Different chemical species show different spatial distributions within the coma. Water vapor appears concentrated near the vertices where edges meet. Carbon dioxide shows enhanced emission along the edges themselves. Dust scattering intensity follows the hexagonal boundary with remarkable precision. If this organization results from random outgassing, it represents a conspiracy of chemistry that strains credibility. Three-dimensional reconstruction using observations from different viewing angles confirms the geometry is not a projection effect. The hexagon maintains its proportions when observed from Earth, from Mars' orbital perspective, and from archived solar observatory data showing completely different angles. This rules out scenarios where a regular structure creates the illusion of geometry through specific viewing geometry. Temporal evolution tracking shows something even more disturbing. Between July and November 2025, as 3I Atlas approached the Sun and activity increased dramatically, the hexagon remained stable. Comets typically show chaotic evolution in their coma structure as different regions activate and fade. 3I Atlas's geometry persisted through 5 months of observation, through changing solar distances, through varying activity levels, as if locked into place by forces stronger than random sublimation physics. We're looking at organized matter, organized at scales where natural chaos should dominate, maintaining precision that defies conventional comet behavior. Nature creates geometric patterns routinely, and the first refuge for astronomers confronting 3I Atlas's hexagon came from crystallography. Snowflakes display 6-fold symmetry naturally. Mineral crystals grow with precise angles dictated by atomic bonding geometry. Perhaps the hexagon simply represents crystalline ice structures magnified to unprecedented but ultimately natural scales. Water ice crystallizes in hexagonal form under the right temperature and pressure conditions. Each molecule bonds to 4 neighbors in a tetrahedral arrangement that, when extended across millions of molecules, produces the 6-sided symmetry we see in every snowflake. The physics is well understood, elegant, and entirely natural. If 3I Atlas formed in the frigid outer reaches of its parent stellar system, pristine, crystalline ice could theoretically preserve geometric patterns from formation. The scale problem arrives immediately. Snowflakes maintain geometric precision across millimeters. The largest ice crystals found on Earth span centimeters. 3I Atlas's hexagon spans kilometers, roughly 8 orders of magnitude larger than any natural crystal structure ever observed. Growing a single crystal to such dimensions requires extraordinarily stable conditions, zero mechanical stress, and timescales that allow atoms to find their optimal positions without disruption. The interstellar journey itself works against crystal preservation. Cosmic ray bombardment continuously damages ice lattices, creating defects that disrupt long-range order. Temperature cycling as the object passes different stellar environments causes thermal expansion and contraction that fractures brittle materials. Micrometeorite impacts over millions of years should pulverize surface layers regardless of their initial structure. Laboratory experiments with comet analog materials provide sobering context. Researchers have created water ice samples under conditions matching the extreme cold of interstellar space, then subjected them to radiation, thermal cycling, and impacts simulating space weathering. Even under carefully controlled conditions, geometric order breaks down within simulated millennia. Natural processes favor disorder, and time guarantees chaos wins. The composition problem deepens the mystery. 3I Atlas isn't pure water ice. Spectroscopy reveals carbon dioxide, carbon monoxide, complex organic molecules, and that puzzling nickel emission without corresponding iron. These chemical impurities act as crystal defects, preventing the uniform atomic arrangement necessary for large-scale geometric patterns. Mixed composition ices form amorphous structures, not crystalline perfection. Thermal modeling shows another weakness in crystal explanations. As 3I Atlas approached the inner solar system, surface temperatures rose from near absolute zero to levels where sublimation becomes rapid. Pure crystalline ice would sublime uniformly, maintaining geometric patterns briefly before disappearing. Instead, the hexagon persisted through months of activity, through temperature gradients that should destroy any pristine crystal structure, through differential sublimation rates. The magnetic field measurements from solar wind monitoring add a final complication. Crystalline ice has no mechanism to maintain geometric stability against the sculpting effects of solar radiation pressure and particle bombardment. Without some organizing force continuously maintaining the structure, natural erosion should blur the edges and round the vertices within weeks of entering the inner solar system. Crystal hypothesis remains possible, but requires coincidences stacking upon coincidences, each individually unlikely, collectively approaching impossibility. Magnetic fields organize matter into geometric patterns throughout the universe. Saturn's famous hexagonal jet stream at its north pole demonstrates how rotating fluids in magnetic environments naturally create six-fold symmetry. Earth's auroral ovals form regular patterns, where charged particles follow magnetic field lines. Perhaps 3I Atlas's hexagon simply represents another example of magnetic organization on a scale we haven't previously encountered. The physics works elegantly in principle. Charged dust grains and ionized gas in the coma respond to magnetic fields, aligning along field lines and creating visible structure. If 3I Atlas possesses an internal magnetic field, perhaps from metallic core remnants or frozen in magnetic materials during formation, the field could theoretically organize surrounding material into geometric patterns matching the observed hexagon. Researchers immediately examined available magnetometer data from solar wind monitoring satellites. If 3I Atlas generates a significant magnetic field, it should create a detectable disturbance in the ambient solar wind as the object passes through interplanetary space. The Parker Solar Probe's magnetic field instruments recorded 3I Atlas's passage through several monitoring zones between September and November 2025. The measurements showed nothing unusual. Solar wind magnetic field. Strength and orientation passed through 3I Atlas's position without the deflections, compressions, or asymmetries that would indicate a substantial magnetic obstacle. Upper limits on any magnetic field associated with the object came in at less than 10 nanotesla at the coma boundary, roughly 100,000 times weaker than Earth's magnetic field at its surface. Such weak fields cannot organize matter at kilometer scales. The magnetic pressure available from 10 nanotesla fields is negligible compared to gas pressure from sublimation, radiation pressure from sunlight, and simple gravitational forces. Charged particles would barely notice such feeble fields, certainly not align into precise geometric patterns spanning the entire visible coma. The temporal stability problem undermines magnetic explanations, even if stronger fields existed. Magnetic field configurations around rotating bodies change constantly. Saturn's hexagon fluctuates in size and shape over seasonal timescales. Earth's auroral patterns shift minute by minute as solar wind conditions vary. 3I Atlas's hexagon has remained geometrically stable for 5 months through constantly changing solar wind environments and varying levels of internal activity. Laboratory experiments with magnetized dusty plasmas show another limitation. Researchers can create temporary geometric patterns by applying external magnetic fields to charged particle clouds. But these patterns dissolve within seconds when the organizing field is removed or disturbed. Maintaining stable geometry requires active field generation and continuous energy input, mechanisms that remain unclear for an inert comet nucleus. The composition argument returns with force. The nickel without iron chemical signature makes standard magnetic field generation problematic. Planetary magnetic fields typically require conductive cores with specific metallic compositions. The unusual chemistry observed in 3I Atlas doesn't match profiles expected from magnetically active bodies, suggesting whatever generates the hexagon operates through mechanisms unrelated to conventional magnetic dynamos. Magnetic organization remains theoretically possible, but observationally unsupported, requiring magnetic field strengths contradicted by measurements and stability mechanisms without known physical basis. Sound cannot travel through the vacuum of space, but vibrations can propagate through solid materials, and these mechanical oscillations can create remarkably geometric patterns in surprising contexts. The phenomenon, called cymatics, demonstrates how vibrating plates covered with sand or powder produce intricate geometric designs, hexagons among them, at specific resonant frequencies. Perhaps 3I Atlas's geometry represents cosmic scale cymatics in action. The theoretical framework builds on established physics of vibrating bodies. Every solid object has natural resonance frequencies determined by its size, shape, composition, and internal structure. When excited at these frequencies, stand-in waves form throughout the material, creating nodes and antinodes, regions of minimum and maximum vibration amplitude. If outgassing occurs preferentially from antinodes where vibration amplitude peaks, the resulting jets could organize along geometric patterns. Calculating the resonant frequencies for a 5-kilometer ice and rock body yields periods in the range of several minutes to hours, depending on assumptions about internal rigidity and composition. 3I Atlas's 18-hour rotation period doesn't match simple resonance predictions, but coupled modes involving both rotation and internal vibration could theoretically produce complex oscillation patterns with geometric structure. The energy source presents the first major obstacle. Resonance requires continuous excitation to overcome damping from internal friction and energy loss through outgassing. Tidal forces from the Sun could theoretically pump energy into the object, but at 3I Atlas's current distance of roughly 1 astronomical unit, solar tides generate stresses orders of magnitude too weak to sustain significant vibrations in a body this massive. Internal heat from radioactive decay might provide sustained energy, but the power available from natural radioactivity in typical comet compositions falls short by factors of thousands. Maintaining resonant vibrations strong enough to organize surface activity requires power inputs comparable to small geothermal systems, mechanisms that remain unexplained for an inert comet nucleus traveling through interstellar space. The outgassing correlation test offers empirical evaluation of resonance theories. If geometric patterns result from vibration modes, outgassing intensity should correlate with predicted antinode locations. High-resolution spectroscopy from November 7th, 2025 mapped gas production rates across 3I Atlas's surface with spatial resolution approaching 100 meters. The data showed enhanced outgassing along hexagonal edges, matching geometric predictions. But the enhancement pattern remained stable over multiple rotation periods, showing no temporal variation expected from resonant oscillations. Vibration modes should produce time-variable intensity patterns as different regions move through nodes and antinodes. 3I Atlas's geometry showed none of this temporal structure. Seismic studies of comets and asteroids provide context. The Philae lander's seismometer on Comet 67P detected no resonant oscillations, despite the comet's active sublimation. The OSIRIS-REx mission to asteroid Bennu found a surprisingly rigid body with damping timescales, orders of magnitude shorter than required for sustained geometric resonance patterns. Resonance offers elegant mathematics, but fails observational tests, requiring energy sources without physical basis, and producing predictions contradicted by the geometry's temporal stability. Complex rotation creates optical illusions that can transform irregular objects into apparently geometric forms when viewed from specific angles. Tumbling asteroids sometimes appear circular or elongated depending on viewing geometry. Perhaps 3I Atlas's hexagon represents nothing more than a particularly convincing projection effect, an irregular nucleus presenting geometric shadows and highlights that fool observers into seeing regularity where chaos actually reigns. The rotation period measurements provide the foundation for this hypothesis. 3I Atlas completes one rotation approximately every 18 hours, based on brightness variations recorded throughout October and November 2025. If the object tumbles chaotically, rather than rotating around a single axis, the changing orientation could periodically align irregular features into patterns that mimic geometric structure. Computer simulations of irregular bodies under complex rotation reveal surprising possibilities. Researchers input randomly shaped nuclei into orbital dynamic software, added realistic surface features like craters and ridges, then calculated how these objects would appear from Earth's perspective during various rotation states. Some configurations produced transient geometric patterns lasting hours or days before the continued tumbling destroyed the illusion. But 3I Atlas's hexagon persists. 5 months of continuous observation from July through November showed the geometric structure remaining stable through hundreds of rotation cycles. Any projection effect would break down as viewing geometry changed with Earth's orbital motion, as 3I Atlas traveled along its trajectory, and as the object's own rotation presented different faces to observers. The mathematics of rotation predict that illusory geometry should flicker in and out of existence, not maintain precise angles and edge lengths across changing conditions. The multi-observatory confirmation delivers the fatal blow to simple rotation explanations. When Earth-based telescopes in Chile observed 3I Atlas simultaneously with Mars orbital assets in November, both viewing angles showed the hexagon with consistent geometry, despite observing from positions separated by tens of millions of kilometers. Projection effects cannot remain consistent across such radically different viewing perspectives. Three-dimensional reconstruction using stereoscopic techniques confirms the geometry is physically real rather than apparent. By combining observations from different locations and different times, researchers built volumetric models of three eye-atlases' coma structure. These models show the hexagonal edges occupying consistent three-dimensional positions regardless of viewing angle, ruling out projection artifacts that would shift position as perspective changed. The photometric analysis adds another constraint. If irregular surface features created the appearance of geometric edges through shadow and highlight effects, brightness should vary dramatically along these apparent edges as solar illumination angle changed with the object's rotation and orbital motion. Instead, the hexagonal boundaries maintain consistent brightness ratios across different illumination geometries, suggesting real physical boundaries rather than lighting tricks. Rotation dynamics can explain many optical illusions in asteroid observations, but three eye-atlases geometry shows none of the characteristic signatures of projection effects. The hexagon remains stable across viewing angles, persistent across rotation cycles, and consistent across independent observational methods. Whatever creates this pattern, it exists in physical reality rather than observational artifact. Light does strange things when passing through clouds of particles with specific size distributions and compositions. Forward scattering, where photons preferentially bounce toward the observer rather than away, can create brightness patterns that don't correspond to actual material distribution. Perhaps three eye-atlases hexagon represents an optical illusion created by dust grains acting as natural lenses, bending and focusing light into geometric patterns that exist only in the observer's eye. The physics of light scattering depends critically on particle size relative to wavelength. When dust grains measure close to the wavelength of visible light, roughly half a micrometer, they enter a regime called scattering, where electromagnetic interactions produce complex angular distributions of scattered intensity. Under very specific conditions, these patterns can include geometric features, rings, and structured brightness that might mimic organized matter. Laboratory experiments with comet analog materials demonstrate the principle. Researchers create dust clouds matching estimated compositions from three eye-atlases' spectroscopic signatures, then illuminate them with laser light while recording scattering patterns from different angles. Some grain-size distributions produce structured scattering with regions of enhanced and suppressed brightness that could conceivably create apparent edges when viewed through telescopes. The wavelength independence test demolishes this comfortable explanation. If the hexagon resulted from scattering by dust grains of specific sizes, the pattern should change dramatically or disappear entirely when observed at different wavelengths. Optical light scattering depends on grain sizes around 0.5 micrometers. Infrared observations at 3 micrometers respond to grains 6 times larger. Radio observations detect scattering from millimeter-scale particles thousands of times bigger than optical grains. Every wavelength shows the hexagon. The James Webb Space Telescope's infrared instruments reveal the same geometric structure as optical telescopes. Archived ultraviolet observations from Hubble show consistent geometry. Even radio interferometry, detecting molecular line emissions, maps gas distributions that follow the hexagonal boundary. This wavelength independence proves the geometry exists in material distribution itself, not in optical artifacts from preferential scattering. the polarization measurements provide additional constraints. Scattered light becomes polarized, with the degree and angle of polarization revealing information about scattering particle properties. If dust lensing created the apparent hexagon, polarization patterns should show characteristic signatures of me scattering with specific angular dependencies. Instead, polarimetry of 3I Atlas from November 10, 2025 shows polarization aligned with the geometric edges themselves, suggesting physical boundaries in material density rather than optical scattering effects. Temporal stability again emerges as the critical test. Dust grain size distributions in active comets evolve constantly as fresh material sublimates from the nucleus, and existing grains fragment through collisions and thermal stress. Any scattering pattern depending on specific grain sizes should fluctuate on timescales of days or weeks as the particle population changes. 3I Atlas's hexagon remained stable through 5 months of observation, through dramatic changes in activity level, and through varying solar distances that should alter dust production rates and grain evolution. Dust can create illusions, but not illusions this persistent, this wavelength independent, or this geometrically precise across changing observational conditions. By November 12, 2025, every conventional explanation for 3I Atlas's geometric structure had failed crucial observational tests. Crystal growth couldn't explain the scale. Magnetic fields weren't strong enough. Resonance patterns lacked energy sources. Rotation dynamics contradicted multi-angle observations. Dust scattering failed wavelength independence. The natural hypothesis space was exhausted, and astronomers found themselves confronting a possibility that seemed to belong in science fiction rather than peer-reviewed journals. The artifact hypothesis emerged not from wild speculation, but from systematic elimination of alternatives. When natural processes cannot account for observed phenomena, and when those phenomena display characteristics associated with purposeful design, scientific methodology demands considering technological explanations, regardless of how uncomfortable they make the scientific community. Geometry itself carries meaning beyond mere shape. Throughout human history, precise geometric forms have served as signatures of intelligence and intentional construction. Natural landscapes show fractals, curves, and irregular boundaries. Engineered structures display straight lines, regular polygons, and symmetrical arrangements. The distinction isn't absolute, but it's statistically powerful. Geometry suggests purpose. The hexagon's precision elevates this suggestion to something approaching an argument. Edge length variations under 2% across kilometer scales exceed what geological processes typically achieve by orders of magnitude. Angular deviations under half a degree strain natural formation models beyond breaking points. When engineers design structures requiring geometric precision, they achieve exactly these kinds of tolerances through active control and feedback systems. 3I Atlas's mass anomaly acquires new significance under artifact interpretation. The disconnect between visible outgassing and missing acceleration suggested either unprecedented mass or unusual physics. If the object contains manufactured structures, internal frameworks or hollow sections could explain density distributions inconsistent with solid ice and rock. Artificial materials might ablate differently than natural ones, producing visible activity without corresponding momentum transfer. The chemical signatures become clues rather than mysteries. Nickel without iron matches certain corrosion-resistant alloy compositions used in high-temperature applications. The carbon dioxide-rich ice could serve as propellant or thermal management medium. Enhanced emissions at geometric vertices might indicate active venting systems or structural joints where different materials meet. Each anomaly previously dismissed as unexplained natural variation transforms into potential evidence of engineering. Statistical arguments sharpen the artifact hypothesis into testable predictions. If 3I Atlas represents natural formation, it should be one example from a continuous distribution of interstellar objects with varying degrees of geometric regularity. If artificial, it might be unique or extremely rare, an outlier separated from natural objects by a gap in parameter space. Future detections by Vera Rubin Observatory will determine which pattern emerges. The burden of proof intensifies rather than relaxes. Claiming artificial origin for an interstellar visitor represents an extraordinary assertion requiring extraordinary evidence. Geometry alone, however precise, cannot prove intentional construction. What's needed are definitive signatures, unambiguous markers that separate manufactured objects from natural ones beyond reasonable doubt. The search for those signatures would drive observational campaigns over the coming months. But first, astronomers needed to understand what function such geometry might serve, if indeed it represented purposeful design. If 3I Atlas represents artificial construction, the hexagonal geometry must serve some purpose. Engineers don't create precise structures for aesthetic reasons alone, especially not structures spanning kilometers that must survive million-year journeys through interstellar space. Understanding potential functions requires thinking like spacecraft designers, while acknowledging we might be dealing with engineering principles beyond current human technology. Solar sail configurations immediately suggest themselves. Light sails use radiation pressure from starlight for propulsion, and geometric precision maximizes efficiency by ensuring uniform force distribution across the sail surface. A hexagonal arrangement could represent 6 triangular sail segments meeting at a central hub, a design that balances structural strength with surface area. The orientation of 3I Atlas's hexagon, tilted 37 degrees from its orbital plane, might indicate deliberate attitude control for thrust vectoring. Thermal management systems represent another plausible function. Spacecraft operating near stars require radiators to dump excess heat into space. Geometric panel arrangements maximize radiative surface area while minimizing structural mass. The hexagon's edges could mark boundaries between radiator segments with different thermal properties, designed to maintain optimal operating temperatures across varying solar distances. Enhanced outgassing at vertices might represent coolant venting or phase change materials, releasing stored thermal energy. Communication arrays offer a third possibility. Large geometric structures can function as phased array antennas, transmitting or receiving radio signals with directional precision impossible for smaller systems. A 4-kilometer hexagonal array could generate extremely narrow transmission beams, or detect faint signals from specific directions while rejecting background noise. The stable orientation maintained throughout 3I Atlas's journey might indicate the array remains pointed toward some distant target. Defensive shielding provides a more speculative but intriguing function. Interstellar space contains hazards ranging from cosmic rays to micrometeorites, traveling at velocities where even dust grains impact with explosive force. A geometric shield structure could incorporate multiple material layers, each optimized for different threat types. The hexagonal arrangement might represent optimal packing geometry for protective panels, while maintaining structural integrity under impact loads. Scientific instrumentation represents the most optimistic interpretation. An interstellar probe designed to study multiple stellar systems might deploy geometric sensor arrays to maximize data collection efficiency. Different hexagon segments could house different instrument types: spectrometers analyzing stellar compositions, magnetometers mapping interstellar fields, particle detectors sampling the medium between stars. The outgassing observed might be active cooling for sensitive detectors, or propellant for minor course corrections. Hybrid functions seem most realistic for any actual interstellar vessel. Modern spacecraft integrate multiple systems into single structures. Solar panels provide power while serving as radiators. Communication antennas double as structural elements. A hexagonal framework could simultaneously function as solar sail, thermal radiator, and instrument platform, with geometric precision serving all three roles through careful engineering optimization. The critical question isn't which function seems most plausible, but rather what observational signatures each function predicts. Solar sails should show optical properties different from natural dust. Radiators should display characteristic thermal emission patterns. Communication arrays might produce detectable transmissions. Defensive shields should show layered structure in radar returns. Each functional hypothesis generates testable predictions that upcoming observations could evaluate. Understanding possible functions focuses the search for definitive evidence, transforming the artifact hypothesis from philosophical speculation into empirical investigation. Determining what 3-eye atlas is made of becomes crucial for evaluating artifact hypotheses. Natural comets consist primarily of water ice mixed with rock dust, frozen gases, and organic compounds. Artificial structures require materials with specific properties, strength to weight ratios, thermal stability, and resistance to space weathering that natural compositions rarely achieve. Spectroscopy provides the only tool for analyzing composition from hundreds of millions of kilometers away. The existing spectroscopic data already hints at chemical peculiarities. The nickel emission without corresponding iron, observed by Very Large Telescope Spectroscopy in August 2025, takes on new significance under artifact interpretation. Terrestrial engineering uses nickel-based superalloys for high-temperature applications, where strength and corrosion resistance matter more than cost. Inconel, Hastelloy, and similar alloys contain nickel concentrations far exceeding iron in specific formulations designed for extreme environments. But spectroscopy of the coma measures only volatiles and dust, material sublimating from the surface, or suspended in surrounding gas. The nucleus itself, where any structural framework would reside, remains hidden beneath this active envelope. Distinguishing between surface coatings and bulk composition requires observations that penetrate the coma or catch the object during periods of reduced activity. Polarimetry measurements from November 15th, 2025 provide indirect compositional constraints. Polarized light reveals information about particle shapes, sizes, and refractive indices that differ between natural and manufactured materials. Natural comet dust shows irregular, fluffy aggregates with polarization properties matching laboratory measurements of primitive carbonaceous materials. 3-eye atlas's polarization signatures show anomalies in specific wavelength ranges, particularly in the near-infrared, suggesting particle populations with different optical properties than typical comet dust. The thermal emission spectrum offers another diagnostic. Different materials radiate heat with characteristic spectral signatures. Metals show high thermal conductivity and emit as nearly perfect blackbodies. Silicate rocks display emission features at specific infrared wavelengths from molecular vibrations. Ice shows distinct absorption bands. Composite materials or exotic alloys might produce thermal signatures unlike anything in natural solar system objects. Spitzer Space Telescope archival data, reprocessed with enhanced techniques in November, revealed subtle emission features in 3 I-Atlas's thermal spectrum that don't match standard comet models. The features appear near wavelengths where titanium alloys and certain carbon composites show characteristic absorption edges. The signal remains tentative, buried near noise levels, but multiple independent analysis pipelines detect the same anomalies. Radar observations scheduled for late November provide the most direct compositional test. Radio waves penetrate dust and gas to reflect off solid surfaces, with return signal strength and polarization, revealing surface roughness and bulk electrical properties. Metals produce strong radar returns with characteristic polarization. Rocky materials show weaker, depolarized returns. If 3I Atlas contains significant metallic structures, radar should detect them unambiguously. The reflectance spectrum across visible and near-infrared wavelengths shows another peculiarity. Natural comet nuclei are among the darkest objects in the solar system, reflecting only 3 to 5% of incident sunlight. 3I Atlas's nucleus appears slightly brighter, reflecting roughly 8 to 10%, suggesting either unusual surface composition or contamination by materials with different optical properties. Materials analysis cannot prove artificial origin, but it can rule out natural composition if observations reveal substances inconsistent with primitive solar system formation or interstellar chemistry. The original mass anomaly that first marked 3I Atlas as unusual now demands re-examination through the lens of geometric structure. An object weighing 33 trillion kilograms, showing active outgassing, but virtually no measurable acceleration, violated natural comet physics. The hexagonal geometry provides a potential resolution if the structure represents controlled propulsion, rather than random sublimation. Solar sails demonstrate how geometric precision enables thrust control impossible with irregular surfaces. Radiation pressure from sunlight exerts force proportional to surface area and reflectivity. A randomly shaped comet nucleus experiences uneven forces that create torques and accelerations in unpredictable directions. A geometric sail structure can balance these forces through careful orientation, producing net accelerations in desired directions, while appearing motionless to distant observers measuring residual perturbations. The tilt angle of 3I Atlas's hexagon becomes significant. 37 degrees from the orbital plane represents neither random orientation nor alignment with obvious reference frames, like the ecliptic or solar rotation axis. But it matches closely with the angle that would null net solar radiation pressure for a hexagonal sail, traveling on 3I Atlas's specific trajectory. Coincidence or evidence of active attitude control remains ambiguous. Thrust vectoring through selective outgassing offers an alternative propulsion mechanism consistent with observed chemistry. If the hexagon's vertices represent controlled venting ports rather than random active regions, precisely timed gas releases could generate forces that cancel or augment solar radiation pressure. The enhanced water vapor emission at vertices, observed spectroscopically, might indicate active thrusters firing in coordinated patterns. The momentum budget calculations become crucial tests. Natural outgassing at the observed rate of 150 kilograms per second, with escape velocities around 440 meters per second, should produce accelerations easily detectable in precision astrometry. The fact that observed acceleration remains below 15 meters per day squared requires either extraordinary mass or momentum cancellation through opposing forces. Geometric propulsion resolves this paradox elegantly. If outgassing occurs symmetrically from multiple vertices with careful force balancing, the net acceleration approaches zero while visible activity continues. Human spacecraft use reaction control systems with exactly this principle, firing opposing thrusters simultaneously to maintain attitude without translating. 3I Atlas might employ the same technique at scales thousands of times larger. Testing propulsion hypotheses requires detecting trajectory changes beyond natural orbital mechanics. If 3I Atlas exhibits post-perihelion acceleration changes, particularly non-gravitational forces that correlate with hexagon orientation rather than solar direction, that would constitute strong evidence for controlled propulsion. Conversely, if the trajectory remains purely ballistic through perihelion passage and beyond, natural explanations regain credibility despite geometric structure. The observation window extends through early 2026 as 3I Atlas recedes from the Sun. Precision astrometry, continuing beyond perihelion, will track whether the object follows predicted gravitational trajectories or deviates in ways suggesting active control. The geometry makes specific predictions about thrust directions if it functions as propulsion system, predictions that upcoming months will test. Solar radiation pressure alone cannot explain the complete absence of non-gravitational acceleration, given the observed activity levels. Something actively stabilizes 3I Atlas's trajectory, and geometry might be the mechanism. Geometry represents universal language, transcending cultural and biological differences. Any technological civilization understands mathematics, recognizes regular polygons, and appreciates symmetry. If 3I Atlas represents an intentional message rather than functional spacecraft, the hexagon itself might constitute the communication, a beacon designed to attract attention through its sheer geometric improbability. The precedent exists in human attempts at interstellar messaging. The Arecibo message, transmitted in 1974, encoded information in binary patterns designed to reveal mathematical and chemical concepts to any recipients capable of detecting radio signals. The Voyager Golden Records carry geometric diagrams explaining Earth's location using pulsar timing maps. Geometric forms serve as attention getters, signals that say, "This is not random. This deserves investigation." A hexagon offers specific advantages as a universal symbol. Six-fold symmetry appears throughout nature in contexts from snowflakes to benzene rings, making it recognizable across different chemical and physical environments. But kilometer-scale precision in space distinguishes artificial hexagons from natural ones unambiguously. The geometry screams artificiality without requiring complex encoding schemes or shared symbolic frameworks. Radio observations intensified following the geometric discovery. The Very Large Array in New Mexico dedicated observing time on November 18, 2025, to search for narrowband transmissions from 3I Atlas across frequencies from 1 to 10 GHz. These wavelengths pass through interstellar space with minimal absorption and represent logical choices for intentional beacons. The search protocols looked for constant frequency signals, pulsed patterns, or frequency sweeps that would indicate artificial origin. The results showed only thermal noise and natural molecular line emissions. No coherent signals, no modulated patterns, no evidence of active transmission from the object itself. Upper limits on equivalent isotropic radiated power came in below 1 kilowatt for narrowband signals, roughly the power of a terrestrial television transmitter. Any deliberate beacon would need to be either extremely weak or operating at frequencies not yet surveyed. Optical SETI observations searched for laser pulses or modulated light that might carry information encoded in intensity variations or color changes. Telescopes monitored 3I Atlas for nanosecond flashes, characteristic of pulsed laser communication. Nothing appeared above background photon noise. If the object communicates through electromagnetic radiation, it does so at power levels or in frequency ranges that remain undetected. The geometry itself might be the complete message. Perhaps, say, the hexagon simply announces, "Look here, something unusual exists," without attempting to convey complex information. The communication value lies in provoking investigation and observation, forcing civilizations to develop technologies capable of detailed study. The true message might only become apparent through close proximity observations. The geometric discovery triggered institutional responses unprecedented in modern astronomy. By November 20th, 2025, space agencies across 3 continents had convened emergency planning sessions to coordinate observation strategies and evaluate mission redirection possibilities. The potential implications of artificial structure in an interstellar visitor demanded systematic investigation beyond normal scientific curiosity. NASA headquarters established a dedicated task force reporting directly to the administrator's office. The group included representatives from planetary science, astrobiology, SETI programs, and mission planning divisions. Their mandate covered 3 priorities: maximize observational data collection, assess feasibility of close encounter missions, and develop communication protocols for potential confirmation of artificial origin. The European Space Agency activated similar coordination mechanisms through its Science Program Committee. Existing missions received authorization to divert resources toward 3I Atlas observations when geometric opportunities arose. Ground-based telescopes under ESA coordination shifted scheduling priorities to accommodate target of opportunity requests from research teams studying the hexagon. International coordination reached levels normally reserved for planetary defense scenarios. The International Astronomical Union established a working group specifically for interstellar visitor characterization, with subcommittees addressing natural versus artificial determination criteria, observation protocol, standardization, and public communication strategies. Daily teleconferences connected researchers across time zones as new data arrived from different facilities. Political dimensions emerged as governments recognized potential implications. Congressional science committees requested briefings on 3I Atlas findings and observation plans. The White House Office of Science and Technology Policy began monitoring the situation, though official statements emphasized scientific investigation over speculation about artificial origins. Similar governmental interest manifested in Europe, Japan, and other nations with space programs. Data sharing protocols received urgent attention. Should preliminary findings remain within scientific community until peer review completion? Or does the potential significance demand immediate public disclosure? Different institutions held different philosophies. Some argued transparency required real-time data release. Others insisted premature announcements risked public confusion if initial interpretations proved incorrect. Media coordination became crucial as news coverage intensified. Space agencies issued joint statements acknowledging geometric observations while emphasizing ongoing investigation and multiple possible explanations. The statements carefully avoided both dismissing artificial hypotheses and endorsing them prematurely, walking a rhetorical tightrope between scientific caution and public interest. Observation scheduling transformed into a complex optimization problem. Multiple facilities wanted access to the target, but telescope time remains finite, and other scientific programs deserved continuation. Priority systems balanced immediate urgency of characterizing 3I Atlas against long-term research commitments to other projects. Some facilities implemented round-the-clock scheduling, unprecedented for non-emergency astronomical observations. The emergency protocols reflected institutional recognition that 3I Atlas had transcended normal scientific curiosity to become something potentially historic, demanding extraordinary coordination and resource allocation, regardless of whether the geometry ultimately received natural or artificial explanation. Mars orbital assets provided the first opportunity to observe 3I Atlas's hexagonal structure from a completely independent viewing angle, offering crucial three-dimensional confirmation that the geometry represented physical reality rather than observational artifact. The Mars Reconnaissance Orbiter repositioned on November the 22nd, 2025, to capture images during the object's passage within 30 million kilometers of the red planet. The geometric structure remained visible and consistent from Mars' perspective. Edge lengths measured from Martian orbit matched Earth-based observations within measurement uncertainties, confirming the hexagon maintained its proportions across dramatically different viewing angles separated by tens of millions of kilometers. This stereoscopic confirmation eliminated any remaining speculation about projection effects or illusory patterns created by specific observational geometry. Three-dimensional reconstruction became possible by combining simultaneous observations from Earth and Mars. Researchers triangulated vertex positions in space, building volumetric models that revealed the hexagon's true spatial orientation and depth structure. The analysis showed the geometric plane sits tilted not just relative to the orbital plane, but also relative to the coma's overall symmetry axis, suggesting the structure maintains independent orientation, regardless of surrounding material dynamics. Unexpected details emerged from the different viewing angle. While Earth-based telescopes observed the hexagon nearly face-on, Mars orbiters saw it at a steeper angle, revealing thickness information invisible from terrestrial perspective. The edges appeared to have vertical extent, rising above or cutting below the surrounding coma material by approximately 200 to 300 meters based on shadow and brightness gradient analysis. The trace gas orbiter's spectrometer captured compositional data from Martian perspective, mapping chemical distributions across the hexagonal structure at wavelengths complementary to Earth-based observations. The nickel emission enhancement at vertices appeared consistent from both viewing angles, ruling out observational artifacts from Earth's atmospheric absorption or instrumental characteristics. The chemical asymmetry was real and spatially correlated with geometric features. Time-coordinated observations revealed dynamic behavior invisible to single observatory monitoring. When Earth and Mars facilities observed simultaneously on November 24th, they detected brightness variations across the hexagon surface occurring on timescales of minutes. These fluctuations showed spatial coherence, with adjacent regions brightening and dimming in coordinated patterns, suggesting large-scale processes operating across the structure rather than random local variations. The Mars observations transformed the geometric discovery from two-dimensional pattern recognition into three-dimensional structural characterization. The hexagon possessed depth, vertical relief, and dynamic behavior that single viewpoint observations couldn't reveal. Whatever created this structure, it extended through space as a genuine physical entity with complexity beyond simple surface markings. The confirmation from an independent planetary perspective eliminated doubt about the geometry's reality, while deepening mystery about its origin and nature. The debate over redirecting NASA's Juno spacecraft toward 3I Atlas reached critical decision point on November 26, 2025. Engineering analysis confirmed the maneuver remained technically feasible through mid-December, but waiting beyond that window would exhaust fuel margins needed for the complex trajectory changes. The space agency faced a historic choice: continue Juno's productive Jupiter science mission, or attempt humanity's first close encounter with an interstellar visitor displaying potential artificial characteristics. The engineering requirements were brutal but achievable. Juno would need to execute a deep gravity assist maneuver during its next close approach to Jupiter on December 8th, firing its main engine at periapsis to maximize the Oberth effect. The burn would consume approximately 80% of remaining fuel reserves, leaving minimal margin for trajectory corrections during the subsequent 4-month cruise to intercept 3I Atlas near its March 16th, 2026 Jupiter encounter. Mission planners calculated intercept distances ranging from 500 to 2,000 kilometers, depending on fuel allocation and trajectory optimization. Closer approaches provided better imaging resolution and more detailed science return, but required higher fuel expenditure and accepted greater navigation uncertainties. The nominal plan targeted 800-kilometer closest approach, balancing science return against engineering constraints. The science case for redirection grew stronger as geometric analysis revealed more structural complexity. Juno's instruments, designed for Jupiter magnetosphere and atmospheric studies, could provide unprecedented close-up observations of the hexagon. The microwave radiometer would measure thermal emission, revealing subsurface temperature structure. The magnetometer could detect magnetic fields at close range, with sensitivity impossible from distant observations. The ultraviolet spectrograph would map auroral emissions, if any existed. Political pressure intensified following congressional hearings on November 23rd, where representatives questioned why NASA hadn't already committed to the mission. Public interest in 3I Atlas had reached levels normally associated with crewed spaceflight programs. Social media campaigns advocated for the Juno redirect under hashtags emphasizing once in civilization, opportunity for potential first contact. The Jupiter science community pushed back hard. Juno had revolutionized understanding of gas giant interiors through precision gravity measurements impossible from any other platform. Extended mission plans promised additional discoveries about Jupiter's deep atmosphere and magnetic field evolution. Abandoning these objectives for speculative interstellar visitor investigation risked sacrificing guaranteed science return for uncertain payoff. NASA administrator convened final decision meeting for November 30th, weighing technical feasibility against scientific priorities and public interest. The announcement would need to come within days to allow time for detailed trajectory planning and spacecraft preparation, before the December 8th maneuver window closed forever. The choice would define how humanity responded to the most anomalous object ever detected entering our solar system, with implications extending far beyond any single mission. While debate raged over Juno's potential redirection, the Parker Solar Probe was already positioned to observe 3I Atlas from the most unique vantage point available, the Sun's perspective during perihelion passage. The probe's Whisper camera system, designed to image solar wind structures and coronal mass ejections, would capture the interstellar visitor as it reached closest approach to our star on the far side from Earth's view. Parker's orbital mechanics placed it within 30 million kilometers of 3I Atlas during the critical late November through early December period, when the object approached perihelion but remained hidden behind solar glare from terrestrial observers. This solar side perspective offered the only opportunity to monitor the hexagonal structure's behavior during maximum thermal stress and activity levels. The first images arrived on November the 28th, 2025, transmitted during Parker's regular data downlink window. The hexagonal geometry remained clearly visible despite the probe's distance, and Whisper's primary design for extended source imaging rather than point-object photography. More significantly, the structure showed no signs of degradation or distortion, despite surface temperatures approaching 200 degrees Celsius as solar heating intensified. Thermal stability at these temperatures challenged both natural and some artificial material hypotheses. Water ice subliments rapidly above 0 degrees. Carbon dioxide ice vanishes at -78 degrees. Even exotic ices like methane and ammonia cannot survive the thermal environment 3I Atlas experienced near perihelion. Yet the hexagon persisted with geometric precision, unchanged from observations months earlier at much greater solar distances. The activity levels revealed another surprise. Outgassing rates increased dramatically, as expected from rising temperatures, but the spatial distribution of activity remained locked to the hexagonal geometry. Enhanced emission continued concentrating at vertices with the same relative intensity patterns observed previously. Random sublimation from a natural comet. Nucleus should show chaotic evolution as different regions activate and fade unpredictably. 3I Atlas's activity followed geometric organization through changing thermal conditions. Whisper's polarization filters detected structured polarization aligned with hexagon edges, confirming earlier ground-based polarimetry from a completely independent platform and viewing geometry. The consistency of polarization signatures across different observational conditions strengthened arguments for physical boundaries in material properties, rather than optical illusions from scattering effects. Parker's magnetometer recorded solar wind interactions during close approach, searching for magnetic field disturbances that would indicate electrical conductivity or active electromagnetic processes. The data showed subtle asymmetries in how solar wind plasma flowed around 3I Atlas, with enhanced deflection near hexagonal vertices, suggesting either localized magnetic fields or charged particle emission concentrated at geometric features. The solar perspective observations confirmed the hexagonal structure survived extreme thermal environments, while maintaining geometric organization of activity patterns, properties difficult to reconcile with passive natural objects, but consistent with actively controlled systems. The James Webb Space Telescope turned its infrared instruments toward 3I Atlas on December 1st, 2025, providing the most detailed spectroscopic analysis yet of the hexagonal structure's chemical and thermal properties. Webb's unprecedented sensitivity and spatial resolution revealed patterns invisible to previous observations, patterns that deepened rather than resolved the mystery of the geometry's origin. Temperature mapping across the hexagon surface showed unexpected uniformity. Thermal infrared imaging at wavelengths sensitive to surface temperature revealed variations of less than 10 degrees Celsius across the entire 4-kilometer structure, despite differential solar illumination angles and varying distances from active sublimation regions. Natural comet surfaces show temperature contrasts of 50 to 100 degrees between sunlit and shadowed areas. 3I Atlas's geometric zones maintained thermal equilibrium, suggesting either efficient heat conduction through subsurface material or active thermal management systems. The near-infrared spectrograph detected absorption features concentrated at hexagon vertices that were absent or much weaker along edges and in central regions. These spectral signatures appeared at wavelengths corresponding to carbon-nitrogen bonds, characteristic of organic polymers and aromatic compounds. The spatial correlation between geometric features and specific chemistry suggested organized material distributions rather than random compositional variations expected from natural formation processes. Mid-infrared observations revealed the most puzzling finding: silicate emission features that dominate typical comet dust spectra appeared suppressed across hexagonal regions, while enhanced in surrounding coma material. This inverse correlation indicated either unusual dust compositions within the geometric structure or preferential removal of silicate particles through processes that left carbon-rich materials behind. Neither pattern matched predictions from natural comet evolution models. The carbon dioxide emission that had characterized 3I Atlas since early observations showed geometric structure at scales. Webb's spatial resolution could finally resolve. Carbon dioxide concentration peaked not uniformly across the hexagon, but in regular patterns, suggesting multiple discrete sources arranged around the perimeter. The spacing between emission maxima measured approximately 700 meters, too regular for random distribution, but lacking obvious connection to any natural sublimation. Physics. Isotopic ratios measured from high-resolution spectroscopy provided another anomaly. The carbon-13 to carbon-12 ratio in carbon dioxide differed significantly from solar system values, confirming 3I Atlas's interstellar origin as expected. But more surprisingly, the ratio varied spatially across the hexagonal structure, with vertices showing enrichment in the heavier isotope compared to edge regions. Isotopic fractionation can occur through various processes, but geometric organization of fractionation patterns had no natural precedent. Webb's infrared revelations showed the hexagon was not merely geometric in shape, but also in chemical organization, with compositional patterns following the structural boundaries in ways that challenged natural formation while stopping short of proving artificial construction. The scientific community fractured into opposing camps by early December 2025 as peer review processes became battlegrounds over competing interpretations of 3I Atlas's geometric structure. What began as healthy scientific debate devolved into increasingly entrenched positions, with researchers' reputations and institutional prestige becoming stakes in a conflict that transcended mere data interpretation. The natural formation camp argued that geometric precision, while unusual, remained within bounds of possible, if improbable, natural processes. They emphasized gaps in understanding of interstellar object formation, potential selection effects in what humanity detects, and the danger of invoking extraordinary explanations before exhausting conventional possibilities. Papers submitted to major journals proposed exotic but natural mechanisms, pressure-driven fracture patterns in primordial ice, standing wave resonances in protoplanetary disk material, or tidal sculpting during close stellar encounters. The artifact interpretation camp countered that accumulated anomalies, mass without acceleration, chemical asymmetries, thermal stability, and now geometric precision exceeded any reasonable threshold for natural coincidence. They argued that scientific conservatism had crossed into willful blindness, that the evidence demanded consideration of technological origins, regardless of philosophical discomfort. Their papers outlined engineering analyses showing how the hexagon's properties matched functional design requirements for various spacecraft systems. Journal editors found themselves in impossible positions. Rejecting artifact hypothesis papers invited accusations of closed-minded gatekeeping. Publishing them risked legitimizing speculation beyond what data could support. Peer reviewers disagreed violently about whether technological interpretations deserved space in mainstream scientific literature or belonged in speculative forums. Some journals implemented special review panels specifically for 3I Atlas submissions. Conference presentations became contentious affairs. The December 10th American Geophysical Union meeting included competing sessions on interstellar visitor characterization, where researchers presented directly contradictory conclusions from identical datasets. Audience questions turned hostile as attendees challenged not just interpretations, but methodological approaches and even professional competence. The traditional collegiality of scientific discourse gave way to accusations of bias, premature conclusions, and insufficient rigor. Social media amplified the conflict beyond academic circles. Researchers found their preliminary findings quoted out of context, their careful caveats stripped away in viral tweets and blog posts. Some scientists received harassment for supporting artifact hypotheses. Others faced ridicule for maintaining natural formation arguments despite mounting anomalies. The public discourse polarized around question of whether scientists were too conservative or too sensational. Funding agencies watched nervously as the conflict escalated. Grant proposals related to 3I Atlas required careful navigation between scientific merit and political palatability. Some institutions discouraged researchers from public speculation. Others saw media attention as opportunity for prominence. The incentive structures of modern academia, where visibility matters as much as rigor, exacerbated rather than resolved disagreements. the academic civil war reflected genuine uncertainty, confronting truly ambiguous evidence. But it also demonstrated how scientific process can break down when observations challenge fundamental assumptions. A third interpretive framework emerged in mid-December 2025 that refused the binary choice between natural formation and technological artifact. The simulation hypothesis proposed that 3I Atlas might represent neither geology nor engineering, but rather a form of organized matter that evolved through selective processes operating across cosmic timescales, a category that challenged conventional distinctions between life and mechanism. The theoretical foundation drew from biomimicry and evolutionary optimization principles. Natural selection produces geometric efficiency throughout biology. Honeycomb structures maximize storage with minimal material. Radiolarian skeletons display geometric precision, rivaling human engineering. Diatom shells exhibit six-fold symmetry with nanometer-scale regularity. Perhaps interstellar space harbors selective pressures that favor geometric organization in ways terrestrial evolution never encountered. Proponents argued that any structure surviving million-year journeys through the hostile interstellar medium must possess extraordinary resilience. Random irregular shapes ablate asymmetrically, tumble chaotically, and fragment under thermal stress. Geometric configurations offer structural advantages: uniform stress distribution, balanced momentum transfer from outgassing, optimal surface area to volume ratios for thermal management. These advantages might drive convergent evolution toward geometric forms. The mechanism remained speculative, but not physically impossible. If primitive self-organizing chemistry operated in interstellar clouds during 3I Atlas's formation, molecular systems capable of templating crystallization or directing material deposition could theoretically create geometric frameworks. These systems wouldn't be alive in conventional terms, but would exhibit some lifelike properties: reproduction of pattern, response to environment, optimization toward stable configurations. Critics immediately challenged the timescale problem. Biological evolution requires reproduction with variation and selection acting over generations. 3I Atlas represents a single object with no evidence of reproductive capacity or population from which selection could operate. Convergent evolution toward geometry requires multiple independent lineages, not isolated specimens. The hypothesis explained nothing without invoking mechanisms as extraordinary as those it sought to avoid. The chemical organization observed by Webb provided weak support for simulation arguments. Spatial patterns in isotopic ratios and molecular distributions might reflect self-organizing chemistry rather than either random geology or intentional design. Laboratory experiments show that certain chemical systems spontaneously form geometric patterns through reaction-diffusion processes. Scaling these mechanisms to kilometer dimensions across million-year timescales stretched plausibility but didn't violate physical law. Astrobiology perspectives found the hypothesis intriguing but premature. The field struggles to define life beyond Earth-based examples, and 3I Atlas might represent a test case for expanding those definitions. But extraordinary claims about novel categories of matter organization require extraordinary evidence, and current observations remained consistent with simpler explanations at both ends of the natural versus artificial spectrum. The simulation hypothesis represented creative thinking outside established frameworks, while highlighting how limited human categories might be. when confronting genuinely alien phenomena. Ancient collision events offered another potential explanation for 3I Atlas's geometric structure, one that remained firmly within natural physics while accounting for unusual regularity. The hypothesis proposed that the hexagon resulted not from initial formation, but from a catastrophic impact billions of years ago that reshaped the object through melting, fracturing, and subsequent re-solidification under specific conditions. Impact physics creates geometric patterns through several mechanisms. High-velocity collisions generate shock waves that propagate through target materials, creating fracture networks with preferential orientations determined by crystallographic axes and stress field geometry. Columnar jointing in terrestrial basalts produces hexagonal fracture patterns when lava cools under specific thermal gradients. Perhaps 3I Atlas experienced impact-induced melting, followed by geometric fracture development during cooling. The scale requirements immediately challenge this explanation. Terrestrial columnar joints span meters at most. The Giant's Causeway in Ireland, among Earth's most impressive examples, shows columns roughly 1 meter across. 3I Atlas's hexagon spans 4 kilometers per edge, roughly 4,000 times larger. Extrapolating fracture mechanics across such scale differences required thermal and mechanical conditions with no solar system precedent. Crater morphology studies provided relevant context. Large impacts create central peak structures, terraced walls, and radial ejecta patterns, but none produce regular polygonal shapes at scales comparable to the entire impact structure. The Oriental Basin on the Moon shows concentric rings from impact-induced faulting, but these circles lack the angular precision observed in 3I Atlas's hexagon. Timing constraints added another difficulty. If the geometry resulted from ancient impact, it somehow survived subsequent billions of years of space weathering, micrometeorite bombardment, and thermal cycling during passages through different stellar environments. Natural erosion preferentially removes sharp edges and straight boundaries, rounding geometric features into irregular forms over geological timescales. The preservation problem became particularly acute, considering 3I Atlas's active sublimation. The object loses thousands of tons of material daily through outgassing, continuously exposing fresh subsurface layers. Any surface geometry from ancient impacts should erode away within thousands of years at current activity levels. Yet, the hexagon persists with edges sharp enough to measure angular precision under half a degree. Computer simulations of hypervelocity impacts on ice rock composite bodies failed to reproduce hexagonal outcomes. Researchers modeled collisions across ranges of impact velocities, projectile sizes, and target compositions. The simulations generated craters, fracture networks, and various irregular morphologies, but never geometric polygons, with the regularity observed in 3I Atlas. The physics simply didn't support hexagon formation through impact processes. Ancient collision events create chaos and irregularity, not geometric precision that persists across cosmic timescales, while the object actively sublimates its surface layers away. The ultimate test for artificial origin required detecting unambiguous manufacturing signatures, features that natural processes simply cannot produce, regardless of time, conditions, or statistical improbability. By mid-December 2025, ultra-high resolution observations began searching for these definitive markers, seams where separate components join, surface textures showing fabrication methods, or structural regularities exceeding what natural formation allows. Adaptive optics systems, pushed to their absolute limits on December 15th, provided spatial resolution approaching 10 meters per pixel across 3I Atlas's hexagonal structure. At this scale, natural geological features should display fractal complexity, with roughness appearing at every resolution level as finer details emerge. Manufactured surfaces show different statistical properties, with smoothness persisting across scale ranges determined by fabrication tolerances. Edge analysis revealed disturbing uniformity. The hexagonal boundaries appeared straight within measurement precision, down to the 10-meter scale, showing no signs of the irregular meandering expected from natural fracture lines or erosion patterns. Statistical tests comparing edge straightness against thousands of terrestrial and planetary geological features placed 3I Atlas in extreme outlier territory, with regularity exceeding 99.9% of natural comparison samples. Surface texture mapping across visible hexagon faces showed another anomaly. Natural surfaces display brightness variations from topographic relief, compositional heterogeneity, and varying degrees of space weathering. 3I Atlas's geometric regions showed remarkably uniform reflectance properties, with variations under 5% across areas spanning kilometers. This uniformity suggested either improbably homogeneous composition or surface processing that removed natural heterogeneity. The search for seams or joints focused on vertex regions where hexagonal edges meet. If the structure represented assembled components, vertices might show construction evidence, gaps between panels, overlapping materials, or fastening mechanisms. Enhanced imaging of vertex regions on December 18th revealed linear features extending radially from several vertices, roughly 200-meter-long structures too straight and regularly spaced to represent random fractures. Spectroscopic analysis of these linear features showed compositional differences from surrounding material. The features appeared enriched in carbon-bearing compounds, while depleted in water ice, opposite the pattern expected from natural sublimation, which preferentially removes volatiles. The composition gradient suggested either unusual formation chemistry or deliberate material placement, creating boundaries between different structural zones. Radar observations from Arecibo Observatory provided subsurface penetration, revealing internal structure invisible to optical instruments. The data showed unexpected regularity in radar return strength across the hexagonal region, with echo characteristics suggesting layered structure at depths of several meters. Natural comet interiors show chaotic mixtures of ice and rock, producing random radar scattering. 3I Atlas displayed organized reflections consistent with parallel interfaces between materials of different electrical properties. None of these signatures definitively proved manufacturing, but collectively they pushed natural formation hypotheses toward breaking points, while remaining tantalizingly short of irrefutable artificial confirmation. One final natural explanation emerged in late December 2025, proposing that 3I Atlas's geometry resulted from tidal forces during a close encounter with a massive stellar object millions of years ago. Gravitational stress during such encounters can fracture bodies along lines determined by the tidal field's geometry, potentially creating regular patterns that survive long after the disruption event. The physics of tidal disruption follows well-established principles. When an object passes close to a massive body, gravitational force on the near side exceeds force on the far side, creating differential stress that pulls the object apart if tidal forces overcome internal structural strength. The Roche limit defines the critical distance where this disruption occurs, varying with the object's density and the primary body's mass. Tidal stress fields possess inherent geometric properties. The principal stress axes align with the line connecting the two bodies and perpendicular directions, creating natural reference frames for fracture orientation. Computer models of tidal disruption show that elongated bodies can develop crack patterns with preferred orientations, sometimes producing segments that appear geometric when viewed from specific angles. But creating a regular hexagon through tidal stress requires extraordinary coincidences. The stress field during disruption must produce exactly 6 fracture planes, meeting at precisely 60-degree angles, a configuration with no obvious connection to the 2-axis symmetry of tidal forces. Random fracture should produce irregular patterns, or at most 2-fold or 4-fold symmetry, matching the stress field geometry. The survival problem, again, became insurmountable. Tidal disruption typically fragments objects completely or leaves them as loose rubble piles, barely held together by weak gravity. 3 eye-atlas displays cohesive structure capable of maintaining geometric precision through active sublimation and thermal stress. A tidally disrupted rubble pile should show continuing evolution as components shift and settle, not stable geometry persisting through months of observation. Identifying candidate disruption events presented another challenge. The encounter would need to occur close enough to a massive object to generate sufficient tidal stress. Yet, the object must survive intact rather than fully fragmenting. White dwarf stellar remnants provide sufficient mass in compact volumes, but 3 eye-atlas's trajectory shows no signs of recent white dwarf encounters. Massive planets could cause disruption at closer ranges. But again, orbital analysis revealed no recent planetary flybys. The chemical organization observed by Webb instruments contradicted tidal explanations. Stress-induced fracturing doesn't selectively organize isotopic ratios or chemical species along geometric boundaries. The compositional patterns required additional mechanisms beyond simple mechanical disruption, mechanisms that remained unspecified in tidal hypothesis formulations. Tidal disruption could fracture objects irregularly, but lacked pathways to geometric precision, chemical organization, or long-term stability, observed in 3 eye-atlas's hexagonal structure. By December 20th, 2025, observations across the electromagnetic spectrum, from radio through gamma rays, had accumulated into the most comprehensive dataset ever compiled for an interstellar visitor. Synthesizing these diverse measurements into coherent understanding required reconciling observations that individually made sense but collectively defied easy interpretation. Radio observations detected molecular emissions organized along hexagonal boundaries. Carbon dioxide, water vapor, and carbon monoxide showed enhanced concentration at geometric edges with spatial resolution approaching 50 meters. The organization persisted across multiple observation epochs, ruling out transient phenomena or data artifacts. Natural sublimation produces chaotic gas distributions. 3 eye-atlas showed geometric order. Infrared measurements from Webb and ground-based telescopes mapped thermal structure, revealing uniform temperatures across hexagon faces despite varying solar illumination. Heat flow calculations showed that maintaining such uniformity required either extraordinary thermal conductivity or active temperature regulation. Natural ice rock mixtures display thermal properties, orders of magnitude too poor to explain the observations. Visible light imaging at highest resolution showed edge straightness and surface uniformity exceeding natural geological comparison samples by statistical margins approaching impossibility. Photometric monitoring revealed coordinated brightness variations across the structure, suggesting large-scale processes rather than independent local activity. The temporal coherence implied communication or physical connection between distant regions. Ultraviolet spectroscopy detected emission lines from ionized species concentrated at hexagon vertices. The ionization requires energy sources beyond simple solar ultraviolet, possibly indicating electrical discharges or particle acceleration mechanisms. Natural comets occasionally show localized electrical activity, but geometric organization of such phenomena had no precedent. X-ray observations from orbiting telescopes detected nothing above background noise, ruling out extremely energetic processes like particle acceleration to relativistic energies or hot plasma generation. The negative result constrained but didn't eliminate various theoretical models involving electromagnetic activity or nuclear processes. Polarization measurements across multiple wavelengths showed consistent alignment with geometric features. The wavelength independence of polarization signatures indicated the organizational principle operated across size scales from submicron dust grains to kilometer-scale structures, suggesting fundamental rather than coincidental geometric control. The contradictions emerged clearly when assembling complete pictures. Thermal uniformity suggested manufactured thermal control, but chemical signatures matched primitive solar system materials. Geometric precision implied intentional construction, but spectroscopic ratios indicated natural formation environments. Activity patterns showed organization, but energy budgets remained consistent with passive sublimation. Radio observations revealed structure, but communication searches detected nothing. Every wavelength added information, but the information refused to resolve into either natural or artificial categories cleanly. The multi-wavelength synthesis demonstrated that 3I Atlas occupied an ambiguous space between classifications, displaying properties from both categories while fitting neither completely. The comprehensive dataset that should have resolved uncertainty instead revealed how limited human conceptual frameworks remained when confronting genuinely anomalous phenomena. The geometry linked every anomaly, connecting mass discrepancies to chemical asymmetries to thermal behavior through organizational principles that demanded explanation regardless of origin. NASA announced the decision on December 1st, 2025. Juno would redirect toward 3I Atlas, executing the most ambitious trajectory change ever attempted for a planetary science mission. The announcement acknowledged enormous risks and uncertain returns, but emphasized that some opportunities justify abandoning guaranteed science for potential breakthrough discovery. The space agency committed to attempting humanity's first close encounter with a geometrically structured interstellar visitor. Mission preparation compressed years of normal planning into 1 week. Flight controllers at Jet Propulsion Laboratory worked around the clock, calculating optimal burn parameters, analyzing fuel margins, and programming spacecraft systems for operations beyond original design specifications. The December 8th trajectory change maneuver would occur autonomously, with Juno executing pre-programmed commands, while radio signals took 46 minutes to travel between Jupiter and Earth. The spacecraft approached Jupiter on its nominal science orbit for what should have been another close pass, gathering magnetic field and gravity data. At 14 hours, 12 minutes UTC on December 8th, Juno fired its main engine at periapsis altitude, deepest in Jupiter's gravity well, where the Oberth effect multiplied propulsive efficiency. The burn lasted 18 minutes, consuming 3,200 kilograms of hydrazine and nitrogen tetroxide propellant. Telemetry confirming successful engine shutdown arrived 46 minutes later, met with cautious celebration at mission control. Initial trajectory reconstruction showed the burn achieved desired velocity change within 2% of predictions. Juno now followed a hyperbolic escape path from Jupiter, aimed toward intercept coordinates, where orbital mechanics predicted 3I Atlas would be on March 16, 2026. The 4-month cruise phase began with systematic spacecraft checkout. Engineers verified all instruments survived the violent acceleration and thermal stress of the trajectory change. The microwave radiometer, magnetometer, ultraviolet spectrograph, and visible light camera all reported nominal operation. Attitude control systems responded correctly to test commands. Communication systems maintained reliable data transmission, despite increasing distance from Earth. Navigation updates refined the approach trajectory as tracking data accumulated. Ground stations around the world measured Juno's position and velocity with precision approaching meters per second, calculating trajectory corrections needed to achieve the planned 800-kilometer closest approach distance. Small trajectory correction maneuvers occurred in January and February, fine-tuning the intercept geometry. By early March, excitement and tension mounted as encounter date approached. The spacecraft remained healthy. 3I Atlas continued along its predicted trajectory, and fuel reserves remained sufficient for final approach navigation. Closest approach would occur at 11 hours 37 minutes UTC on March 16, 2026, with Juno passing 3I Atlas at relative velocity of 12 kilometers per second. The mission execution had succeeded in reaching this point. Now came the crucial test. What would instruments reveal during those few hours of close proximity to the geometric mystery? The first high-resolution images arrived at Earth on March 16, 2026, at 13 hours, 23 minutes, UTC, 1 hour, 46 minutes after Juno's closest approach to 3I Atlas. Mission control fell silent as processed imagery appeared on display screens, revealing details no telescope could resolve from hundreds of millions of kilometers away. What they saw transformed speculation into certainty, while raising questions nobody had anticipated. The hexagon was real, undeniably real, but it wasn't what anyone expected. The geometric structure represented neither simple surface features nor a solid framework, but rather a complex hybrid that defied easy categorization. The edges consisted of raised ridges approximately 300 meters high and 50 meters wide, standing above surrounding terrain like walls, defining enormous hexagonal sections. Surface texture within each hexagonal face showed remarkable smoothness at Juno's resolution limit of 5 meters per pixel. No craters, no boulders, no irregular features that characterize natural comet nuclei. The faces appeared processed, as if swept clean or deliberately smoothed, through mechanisms that removed normal surface roughness. Natural sublimation creates chaotic pits and irregular terrain. 3-eye atlas displayed order. The vertices where edges met revealed the most stunning details. Each junction contained circular structures approximately 100 meters in diameter, darker than surrounding material, and showing concentric rings suggesting depth or layering. Enhanced contrast imaging revealed these structures extended below the surface, possibly shafts or vents penetrating into the nucleus interior. The regular spacing and identical morphology of 6 vertex structures exceeded any reasonable natural coincidence threshold. Compositional mapping from the ultraviolet spectrograph showed sharp transitions at edge boundaries. Ridge structures contained enhanced concentrations of carbon-bearing materials, while hexagonal faces showed ice-rich compositions. The compositional dichotomy suggested different formation processes, or emplacement mechanisms, for geometric features versus background material, inconsistent with uniform accretion models. The magnetometer detected organized magnetic fields during closest approach, with field strengths reaching 200 nanotesla near vertex structures, 20 times stronger than upper limits from earlier distant observations. The fields showed dipole geometry aligned with vertex positions, indicating either magnetized materials concentrated at geometric junctions or active electromagnetic processes generating localized fields. Thermal imaging revealed another surprise. The vertex structures radiated excess heat compared to predictions from solar illumination alone. Temperature differences of 30 to 40 degrees Celsius suggested internal heat sources, possibly radioactive decay concentrated in vertex regions, or residual thermal energy from some process that created or maintains the structures. Juno's 800-kilometer flyby lasted only 7 minutes at closest approach, ranges under 2,000 kilometers. The data returned in those minutes proved the geometry was physically real, structurally complex, and organized at scales and with precision that shattered natural formation paradigms, while stopping just short of proving technological construction. The first high-resolution images arrived at Earth on March the 16th, 2026 at 13 hours, 23 minutes, UTC 1 hour, 46 minutes after Juno's closest approach to 3-eye atlas. Mission control fell silent as processed imagery appeared on display screens, revealing details no telescope could resolve from hundreds of millions of kilometers away. What they saw transformed speculation into certainty while raising questions nobody had anticipated. The hexagon was real, undeniably real, but it wasn't what anyone expected. The geometric structure represented neither simple surface features nor a solid framework, but rather a complex hybrid that defied easy categorization. The edges consisted of raised ridges approximately 300 meters high and 50 meters wide, standing above surrounding terrain like walls defining enormous hexagonal sections. Surface texture within each hexagonal face showed remarkable smoothness at Juno's resolution limit of 5 meters per pixel. No craters, no boulders, no irregular features that characterize natural comet nuclei. The faces appeared processed, as if swept clean or deliberately smoothed, through mechanisms that removed normal surface roughness. Natural sublimation creates chaotic pits and irregular terrain. 3-eye atlas displayed order. The vertices where edges met revealed the most stunning details. Each junction contained circular structures approximately 100 meters in diameter, darker than surrounding material and showing concentric rings suggesting depth or layering. Enhanced contrast imaging revealed these structures extended below the surface, possibly shafts or vents penetrating into the nucleus interior. The regular spacing and identical morphology of 6 vertex structures exceeded any reasonable natural coincidence threshold. Compositional mapping from the ultraviolet spectrograph showed sharp transitions at edge boundaries. Ridge structures contained enhanced concentrations of carbon-bearing materials, while hexagonal faces showed ice-rich compositions. The compositional dichotomy suggested different formation processes or emplacement mechanisms for geometric features versus background material. The magnetometer detected organized magnetic fields during closest approach, with field strengths reaching 200 nanotesla near vertex structures. The fields showed dipole geometry aligned with vertex positions, indicating either magnetized materials concentrated at geometric junctions or active electromagnetic processes generating localized fields. Thermal imaging revealed vertex structures radiated excess heat compared to predictions from solar illumination alone. Temperature differences of 30 to 40 degrees Celsius suggested internal heat sources, possibly radioactive decay concentrated in vertex regions or residual thermal energy from processes that created or maintained the structures. Juno's flyby proved the geometry was physically real, structurally complex, and organized with precision that shattered natural formation paradigms, while stopping just short of proving technological construction. Juno's close-up observations forced fundamental reassessment of every hypothesis about 3I Atlas's origin and nature. The raised ridges, smooth faces, circular vertex structures, compositional boundaries, and organized magnetic fields composed a pattern that natural formation struggled to explain, while artificial construction remained unproven. Integration of all evidence pointed toward uncomfortable conclusions. The mass anomaly now made physical sense. If the hexagonal ridges represented structural frameworks enclosing less dense material or partially hollow sections, the unusual density distribution could explain why visible outgassing produced minimal acceleration. The framework might contain the bulk of the object's mass, while surface sublimation affected only thin outer layers, creating observed activity without corresponding momentum transfer. The chemical asymmetries aligned with structural features. Enhanced carbon compounds at ridges suggested either concentrated organic materials or deliberate compositional variation serving functional purposes. The nickel without iron emission pattern might reflect unusual metallurgy in ridge structures, alloy compositions optimized for properties other than natural abundance ratios. The thermal stability across extreme solar distances became explicable if the structure included active or passive thermal management. The ridge geometry could facilitate heat distribution through high conductivity materials, or the smooth faces might consist of materials with specific thermal properties that maintain temperature uniformity through varying illumination conditions. The geometry itself, the precise angles and edge lengths, no longer stood as isolated anomaly, but as organizing principle connecting every other unusual characteristic. The hexagon wasn't merely shape, but functional architecture, whether created by natural processes operating through principles we don't yet understand, or by technological civilization applying engineering solutions to interstellar travel challenges. Yet, definitive proof remained elusive. No obvious propulsion systems appeared in imagery. No manufactured components showed unambiguous construction signatures. No transmissions emerged during close approach. The vertex structures might be natural vents, organized by geometric stress patterns. The compositional boundaries could reflect unusual but natural formation chemistry. The magnetic fields might result from magnetized materials rather than active generation. The origin question fractured into more specific puzzles. If natural, what processes create kilometer-scale geometric precision in the hostile interstellar environment and maintain it across eons? If artificial, what civilization builds such structures, for what purposes, and why send them through interstellar space without obvious communication attempts? The Juno data eliminated easy answers while confirming that 3I Atlas represented something extraordinary, regardless of origin category. Whether natural wonder, demonstrating principles beyond current understanding, or technological artifact from unknown builders, it demanded explanation that current science couldn't provide. The geometry remained persistent and inexplicable, challenging astronomy to expand its frameworks or acknowledge limits of present knowledge. The implications of 3I Atlas's geometric structure extended far beyond single object characterization into fundamental questions about how science approaches anomalous observations, and what discovering either exotic natural processes or technological artifacts would mean for humanity's cosmic perspective. If natural processes created the hexagon through mechanisms science doesn't yet understand, the discovery would revolutionize fields from planetary formation to materials science. New physics operating in interstellar environments could explain geometric organization, suggesting principles about self-assembly, pattern formation, or matter organization that terrestrial experience never revealed. The discovery would prove that billions of years and cosmic scales enable phenomena impossible in human laboratories or solar system observations. Research priorities would shift dramatically toward understanding these exotic processes. How does matter organize geometrically across kilometer scales? What role do magnetic fields, radiation pressure, or quantum mechanical effects play in creating structure? Can these principles apply to other astrophysical contexts, from planet formation to galaxy evolution? The questions would drive decades of theoretical and observational research. If artificial construction proved correct, the paradigm shift would dwarf any previous scientific revolution. Confirmation of technological civilization beyond Earth would answer humanity's oldest question about cosmic solitude while raising countless new ones. Who built it? When? For what purpose? Are they extinct or still active? How common are technological civilizations in the galaxy? SETI programs would transform from speculative searches to urgent investigations of demonstrated reality. If one artifact exists, others likely do. Detection strategies would expand beyond radio signals to include geometric anomalies, unusual orbital characteristics, and spectroscopic signatures of manufactured materials. The Vera Rubin Observatory's upcoming survey would search not just for natural interstellar visitors, but potential technological objects among them. Planetary defense considerations would acquire new urgency if technological artifacts pass through solar system regularly. While 3I Atlas posed no collision threat, future visitors might. Understanding whether such objects represent passive derelicts or actively controlled vehicles becomes crucial for assessing risks and opportunities. Astrobiology would face complete reconceptualization. The field currently focuses on detecting microbial life or biosignatures in exoplanet atmospheres. Confirmed technosignatures would prove that life not only exists elsewhere, but evolves toward technological capability, suggesting intelligence and civilization might be common outcomes of biological evolution rather than rare accidents. The consequences reach beyond science into philosophy, theology, and human self-understanding. Cosmic loneliness ends, but so does uniqueness. Humanity joins a larger context of technological species, navigating existence across galactic scales and timescales, measured in millions or billions of years. 3I Atlas forced contemplation of futures radically different from presents, regardless of which explanation ultimately proved correct. 3I Atlas continued its journey outward from the Sun through late 2026, gradually fading from view as distance increased and activity declined in the cooling environment beyond Mars' orbit. Final observations in September tracked the object passing Jupiter's orbital distance, still maintaining its geometric structure visible in last high-resolution images before it became too faint for detailed study. The hexagon persisted. Through perihelion passage, through maximum thermal stress, through thousands of tons of sublimated material, the geometric precision remained unchanged from first discovery in November 2025. Whatever created or maintained that structure proved resilient beyond any natural process astronomers could confidently invoke. The accumulated data filled archives that researchers would analyze for decades. Every wavelength observation, every spectroscopic measurement, every image from dozens of telescopes composed the most comprehensive dataset ever compiled for an interstellar visitor. Yet, comprehensive data hadn't resolved fundamental questions about origin and nature. The geometry remained inexplicable, suspended between natural wonder and technological artifact. Future observations became impossible as 3I Atlas receded into the darkness between stars. By late 2027, even the most sensitive telescopes would lose detection capability as the object traveled beyond 10 astronomical units, and activity ceased entirely. Humanity's window for studying this mysterious visitor was closing, perhaps forever. No mission could catch it now. No telescope could track it much longer. The lessons extended beyond this single object. The Vera Rubin Observatory began operations in 2026, immediately detecting candidate interstellar visitors at rates of several per year. Most showed irregular shapes and typical comet behavior. None displayed geometric structure remotely approaching 3I Atlas's precision. The comparison made clear how exceptional this visitor truly was, an outlier among outliers. The geometric structure became symbol for how the universe continues surprising us, presenting phenomena that challenge assumptions and demand intellectual humility. Science progresses through willingness to confront observations that don't fit existing frameworks, whether those observations ultimately reveal new natural principles or confirm technological civilizations beyond Earth. 3I Atlas taught astronomy that geometry matters, that precision demands explanation, and that the space between stars harbors mysteries we've barely begun to catalogue. Its silent passage through our solar system asked questions we couldn't answer, but forced us to acknowledge how much remains unknown. The hexagon persisted in memory and data archives long after the object itself vanished into interstellar darkness, a geometric puzzle that might never be fully solved, but would forever change how we think about what drifts between the stars.